work? We see them on so many vehicles around us, like our drones, underwater propulsion systems like this one or that one. Yet the theory behind propellers is one of the most complex issues in practical hydrodynamics. Very often, boat propeller manufacturers or propeller manufacturers in general give us this explanation that it works like an ordinary screw. And you grab a piece of soft material, you push it through, and when you rotate it, it creates motion this way. So people assume that because it works like a screw, and even propeller manufacturers give us a parameter which says how much this thing moves forward per one full turn, which is 360 degrees. They call it a propeller pitch. So they say it works like a screw and it has a propeller pitch. People assume that this explanation is true, it's valid. And actually, it's a huge simplification. So let's talk how this guy really works. Good Monday, Amphinauts and DPV enthusiasts. This is Marek with Amphi Americas, and today I will be talking about propellers. How do they work? We spent our last several episodes talking about biomechanics, and it's probably time to dig into this most important issue, which is the propellers. So before we start, let's take a look at existing propellers. We see them everywhere. We see them on boats, airplanes, airboats, as you can see in this Vietnam era picture, snowmobiles, and even we see them in vehicles which are meant for space exploration. You're skeptical, I know, but take a look at this picture. It's a helicopter designed for Mars exploration. And this one is a submarine with thrusters, which is designed for Jupiter's moon exploration, Europa. So you can see that it's a very popular solution. And if you ask me, propellers are with us for good. They're gonna stay as a very convenient solution to a propulsion question, and we'll be using them always in slow moving vehicles. So before we talk about the theory behind propellers, let's take a look at a history of propellers. So actually the theory came after the first implementation. The first implementation happened in 1775 when David Bushnell built something which was called a boat screw and implemented this propulsion system into his underwater vehicle concept, which was the first submarine, our famous turtle. In theory, the systematic approach came later, almost like 100 years later, when Rankine and Freud developed the first theory of propellers, which was called a momentum theory. It was a kind of like a crude understanding of how propellers work. It wasn't very helpful in practical design efforts, but it opened the gates for further research and theories. And the first fundamental theory, which was useful, and it's useful till now, was developed by Freud again in 1878. and it's called blade element theory. And we're going to use this theory to explain how propellers work. So I'm going to explain this propeller theory in 2 steps. Step number 1 will be to show that fundamentally a propeller is a wing. And the second step will introduce necessary modification to this wing, which will make it more efficient and stronger. So let's start with this wing concept. So I built something which with a little bit of imagination we can take as a wing. So you have a left wing and a right wing here. They have a certain profile here we spoke about earlier. And of course, when this design moves through the water or air or any fluid, it creates a positive pressure at the bottom here. You see positive pressure on one side, right? And negative pressure on the other side. We see here the leading edge here and the trailing edge here. So if we move this thing at a certain angle of attack, it will create positive pressure here underneath and negative pressure at the top. If you are not certain how it works, there's a link to our previous videos which explains this phenomenon. But basically this is how a regular wing works, right? We fly it through the air this way and it creates a lift force which goes this way. Positive pressure underneath, negative pressure here, negative pressure here, right? Now let's do the following. Let's twist this. Let's do a little bit of innovative engineering here. Hold on. All right. There we go. So let's see. Right now we have this wing at a slightly different configuration, right? So you see that a leading edge of this side is here and the leading edge of this side is here. This is the trailing edge and this is the trailing edge. So right now, to fly this wing and this wing together, I have to move it this way, right? I have to rotate it. What happens when I rotate it? Well, I fly this wing and this wing in a circle, right? So if I still keep this angle of attack, I'm going to create positive pressure on one side of this device and negative pressure on the other side, thus the whole thing will move. So if I fly those two wings in this fashion, it will be pushed by this lift force this way. Okay, so this is actually how the Wright brothers thought about the propeller. They understood this, that it's fundamentally a wing which flies in a circle. Now, when you take a look at the actual propeller here, you will notice that there's a difference between this one and this one. The difference is that each wing on this one is twisted. Well, and when you look at this wing, you will notice that something interesting, that each section of this wing will fly with a different speed. And actually this thing, the different speed at each section at different distances from the axis, is what makes this design more efficient when you twist it. But for that, to explain this, I need our whiteboard. Let's discuss this rotating wing situation and what are the implications for our design of this configuration. So let's take one wing, one blade of a propeller. Usually propellers have 2 or 3 or 4 blades, but theoretically you could make it work with just a single blade.
There are also propellers which have more than 4 blades, but they are really special cases. But let's take a look at a single blade, and of course can be replicated to other blades as well. So we have this blade, which is, as we realized recently, it's just a wing with a leading edge and trailing edge here, and it rotates about this point. Of course, those cross sections or strips of this wing will be flying at different speeds when we rotate it with a certain rotational speed omega, because they are at different distances from the axis. So you see that this red strip here is at R1, the blue one is at R2, and the red one again here is at R3. So when we rotate it with omega, this one will move the slowest, this one move a little bit faster, and this one will move the fastest. Let's take a look how the angle of attack looks for each cross section. And to understand the angle of attack, we can not only consider this rotational speed omega, we also have to consider that we have this vector v. This is the speed at which our vehicle is moving. So we have two vectors. One which is coming from this direction. It will be a speed which is omega times the radius, omega times r1 for this section. And we have a vector v, which is the velocity of the vehicle, or the velocity of air which is moving through this propeller, okay? And this will be our v. So if we take those two vectors, the actual vector at which the air hits the blade is this vector w, which is a sum of v and omega times r1. Now you see that you have to adjust your angle of attack to this vector, not to omega times r1 or v, but to something which is a sum of those two. In order to figure out how to adjust this angle beta, we can go back to this graph, which shows us the relationship between the angle of attack and the coefficient of lift. And we see from this graph that there is an optimal position, optimal angle of attack at which the coefficient of lift is the highest. So we would like to be around this angle. Yeah? So let's set it to beta here. Let's move one notch up to this radius of R2. This is our blue graph here. So you see that we still have this velocity v, the same as we had here, because it's the velocity of air going through the propeller. That's fine. But this velocity, omega times R2, is greater than this velocity, right? So the W will be slightly different. The W will be a little bit longer and skewed this way. So for this particular vector, if we want to keep things optimal, here again, we have to keep the same angle, but because the vector W changed, we have to change our angle here. And you may think, well, it's a simple thing to do, you would be right, but you have to do it for each cross section of the blade, right? And the final cross section R3 shows us the same thing. This omega times R3 gets even longer, so the vector W gets a little bit different. It again is skewed more to this side and it's longer, and we have to change the angle of here to keep it at this optimum. This optimization parameters, they may involve more than just being at the highest coefficient of lift, but for the sake of this discussion, let's just keep this one to simplify things. So you see that each cross section has to have a different angle. And this is what makes the blades on the propeller twisted. So this is the second step of my explanation, where we modify the wing, the rotating wing, by twisting it, and we use principles like these to figure out what the twist should be. I tried to keep the same angle on all three graphs here, so the beta is the same here, here, and here. It's difficult to see, but actually it's the case. I'm going to show you that this is actually the case. So you see that this angle here is the same as this angle here, is the same as this angle here, right? So this makes those three cross sections twisted in respect to each other. And this is why a regular a propeller blade is also twisted. So as we go from the center of rotation, from the axis out, we have to twist every single cross section in order to stay at a certain optimum level of our lift. There's one caveat to my explanation, and you probably noticed that when I was explaining this, I assumed a certain omega and I assumed certain V. So if you do this optimization, you actually have to assume the conditions for your propeller. And the conditions would be the speed, and the conditions would be the RPMs, the omega. So for those conditions, your propeller will be optimal. This is why we have propellers for very fast boats or airplanes, and we have propellers which are designed for slower moving boats, but they have more oomph, they are stronger. So this boils down to assuming different V and omega for this type of analysis. One more thing which is maybe interesting, a very modern propellers, they can actually adjust the angle of the blade. So you can have multiple points where your blade is optimal. So for fixed angle of your blade, you're always designing for a certain V and certain omega. It does not mean it won't work for other, but it will be less efficient and weaker. But also you can build a propeller, of course it's mechanically more complex, but possible, which has adjustable angles for the blades. Thus you can shift those angles of attack for different omegas and different velocities, if you will. I've never seen a blade which can adjust separately the angles for each section. That would be probably the best propeller ever, but who knows, maybe you will invent something like that. So I hope you liked this video. It was probably the most complicated so far. If you like it, give us a like, sign up, subscribe. Visit our website where we explain our novel underwater propulsion system, Amphi. And of course, visit us on Facebook. We have a lot of fans over there, and they would like you to join them. And see you, of course, see you next time.